Here you go. All right. I guess we can start. So welcome everyone to the December edition of the One World Mathematics of Climate seminar series. Last time in 2023, already as an announcement, we won't do January because the first Tuesday in January is still holiday in some countries. So the next time will be February. But so for today, we are really glad we have Martin Rypdal with us, who is, yeah, it's one of these lucky cases when mathematicians become interested in climate science. It's always like, yeah, it's a it's very good, I think. Martin has made very important contributions across several fields of applied math, including dynamical system theory, statistical mechanics, response theory, self-organized criticality, and for, I don't know, maybe 7-8 years has developed an interest in climate. He's also worked on other things like epidemiology and so on, but since 7-8 years there's a really sort of like a persistent interest and also persistent flow of very nice research in applying concepts from applied math in the climate sciences. And I'm really happy that we could win Martin for a talk today, where he will talk about climate sensitivity and early warning signals, and give his perspective on these things. And yeah, so with that, floor is yours, Martin. Very much looking forward to this.
So thank you for that nice introduction. Let me see. Yeah, you see the slides?
Yes.
Yep, perfect. Yep. Yeah, so thanks for inviting me. The title of my presentation is From Climate Sensitivity to Early Warning Signals. And I have this plan to divide my presentation into 3 parts. The first part, I'll just talk a little bit about, the underlying idea behind early warning signals, this relation between fluctuations and response, more specifically between fluctuations and the sensitivity of a system. And then in the second part, I will show you some ideas that have been proposed for how to either estimate or constrain equilibrium climate sensitivity from time series data. And in the last part of the presentation, I'll try to combine these 2 first parts to show you maybe some interesting ideas. There won't be a lot of advanced mathematics, but there will be some ideas that at least I think are interesting. So I'll dive right into this first part, talking about early warning signals. The idea behind this, I think, is best illustrated using very simple models. So let me just here consider a nonlinear ordinary differential equation. I'm thinking here of x as just a scalar variable, and you have this nonlinear function f of x. And then I have this additive parameter f, which I will sometimes refer to as the control parameter of the system, or sometimes I'll refer to it as forcing, depending a little bit on the context. So what we are often interested in if we have a system like that is, equilibrium points, fixed points of the system. You find these fixed points by just putting the right-hand side of the equation equal to 0. You can have a situation like the one I sketched below here, and just from this figure, you can see that this fixed point x star is a stable equilibrium. And then if we want to study this, what we typically do is that we linearize around the fixed point. So we introduce this anomaly delta x minus x star. And then I introduce this parameter lambda, which is like the negative of the eigenvalue of this system. It's this slope of the nonlinear function at the fixed point. And then the linearized equation is just this simple first order ODE. If I add noise to this system, I get like a stochastic differential equation. If this is Gaussian white noise, I get a well-known stochastic process that's called the Ornstein-Uhlenbeck process. This is a stationary Gaussian process. It's completely defined by its covariance, which decays exponentially with a rate that is inversely proportional to this feedback parameter, and also the variance of the fluctuations of the linearized system are inversely proportional to this feedback parameter. The next question we can ask is, what is the sensitivity of the system? There are several definitions of sensitivity. The definition I give here is what we call equilibrium sensitivity. And when I say sensitivity, I mean sensitivity to the control parameter. So if we make a change in the control parameter, how much will the equilibrium state, how much will the fixed point change? So the natural definition is this dx star df. But since the x star is the root of the right-hand side of the equation, we can do some calculus here and see that actually the sensitivity is inversely proportional to this feedback parameter. Now, we recall from the previous slide that the variance of the fluctuations of the linearized system was also inversely proportional to the feedback parameter. So that gives us this fluctuation response theorem, which says that the variance of the fluctuations of the linearized system is proportional to the equilibrium sensitivity of the system. Moreover, the autocorrelation function of the fluctuations decay exponentially with a characteristic timescale that is proportional to the equilibrium sensitivity of the system. Now, this relation between sensitivity and fluctuation is particularly useful if we have a situation that looks like this. So imagine that we're studying some component of the climate system or some ecosystem, and it's described by a model of this kind. And we find that there's a range of values for the control parameter where you have multiple fixed points. So the standard situation is the one that I sketched here. There's a range of f values where you have two stable fixed points indicated in red here, separated by an unstable fixed point shown in blue color. There are two bifurcations here, saddle node bifurcations, where the stable fixed point and the unstable merge. And you can have critical transitions from one stable state to the other. And it's clear from the figure here that the equilibrium sensitivity of the system is increasing as you're approaching these critical points, because a given change in the control parameter will lead to larger and larger changes in the equilibrium state. And this should be reflected in the fluctuations around this fixed point. And you see that in the figure to the right, where I just made a simulation. Slowly increasing the control parameter, you're approaching this critical point, and you can just by eye see that the variance of the fluctuations is increasing. And maybe you can also see that the fluctuations are slowing down. The characteristic correlation length is increasing as you approach this critical point. So if we're interested in detecting early, getting some early warning signals for critical transitions, we might look for these signatures in the fluctuations. So what people typically do is they compute variance and autocorrelation in running windows and see if there's if you can detect an increase in these statistical quantities. Now, the formula that I showed you, this relationship between sensitivity and variance, it doesn't hold in general. Here's a simple counterexample, what we call a nonlinear two-box model, where I've just added a second variable x2 here that's linearly coupled to the first variable x1 through this coupling coefficient kappa. Now, to find the fixed points of this system, you just put x2 equal to x1, and then put the right-hand side of the first equation equal to 0. Then you find the fixed points as you did before. You can linearize the system, which introduces this feedback parameter lambda, and you can define the sensitivity in the same way that you did before, and it's inversely proportional to this feedback parameter. However, if you do the math here, the formula on the right-hand side shows the variance of the fluctuations of the linearized system, and the variance of the first variable, and it's only proportional to the equilibrium sensitivity of the system if kappa is small. If kappa is large, the variance can be largely unchanged, even though the sensitivity of the system is increasing. And you can illustrate this by a simple simulation. Here I simulated from this model with a small value of kappa. You can clearly see the increased fluctuation level as you're approaching the critical point. However, if I run the same simulation with a larger kappa, you see that this increase in the fluctuation level is less pronounced, and in this case, it's going to be harder to detect early warning signals. An alternative definition, a completely equivalent definition of equilibrium sensitivity, is to say that we make an instantaneous change in the control parameter and then evaluate the change in the state variable as time goes to infinity. So it's the asymptotic change in the state variable x following an instantaneous response in your control parameter. It's the asymptotic change in the state variable because you want the system to converge to a new equilibrium. However, in some situations, this may take very, very long. It may take, say, thousands of years, and you might not be interested in what's happening on these very long timescales. You might be more interested in what's the sensitivity of your system on, say, a 100-year timescale. What you can do then is you can just simply define the transient sensitivity to be the change in your state variable after, say, 100 years after you make the instantaneous change in your control parameter. This can be illustrated geometrically. So what I show you here is kind of the geometrical interpretation of the equilibrium sensitivity in a bifurcation diagram. So you make a small change in your control parameter, and you evaluate the response in your state variable after a very, very long time when you have converged to an equilibrium state. However, if your system has some high inertia, you may have some transient dynamics. I'm just illustrating it like this. And if you evaluate after a finite time, you might not be in equilibrium. You might be in a different state. And so the transient sensitivity on this time scale is given by the slope of this line that I show you here. Now we can plot lines like that for different values of the control parameter. It will give you a diagram that looks something like this. So this is the system that I showed you before, and now I evaluate my transient sensitivity on a very short time scale. The slopes of the blue lines indicate the sensitivity of the system on this time scale. And what you observe is that even though you're approaching a critical transition, the blue lines are more or less parallel to each other. So the sensitivity of your system is not changing. And so using transient sensitivity defined for this time scale is not going to help you much in detecting early warning signals because it's not changing as you're approaching your critical point. However, if you increase your time scale, you start to see a change. You might detect some early warning signals. And of course, if you go to sufficiently long time scales, there is equality between the transient sensitivity and the equilibrium sensitivity. All right, so that was some kind of basic setup. What I'm going to do now is that I'm going to skip to the question about climate sensitivity. And the point here is to show you that the concepts are very similar to what I just discussed. So the definition of climate sensitivity, I mean, it's a very practical definition if you're a climate modeler, because it's basically related to specific experiments that they do in climate models where you instantaneously double or quadruple the concentration of CO2 in the atmosphere. And then ideally you want to evaluate the corresponding temperature change when time goes to infinity. So when you converge to a new equilibrium for our planet at a higher temperature. You can either give the equilibrium climate change in degrees Kelvin, just the temperature increase corresponding to a CO2 doubling, or you can divide by the radiative forcing corresponding to a doubling of atmospheric CO2, which is around 3.5 watts per square meter. So this is the figure to the lower left shows one such experiment from the NOR-ESM climate model. There's an instantaneous quadrupling of atmospheric CO2. And now what you see is that it takes a very, very long time before it converges to a new equilibrium, thousands of years. And running a climate model for that long is very expensive. Usually the runs that we have are like 150 years long, and you haven't converged to a new equilibrium. And there's a technique that can be used in climate models to still estimate the climate sensitivity. Is called the Gregory plot. It's shown to the right here. What you do is that you have data on this variable n in climate model, which is the radiative imbalance at the top of the atmosphere. Immediately after CO2 doubling, this will have a large value because you are not in equilibrium, but as you're approaching equilibrium, balance will be restored, and so this n will converge to 0. And so even though you don't have enough data to track this change until you have balance, people make this linear extrapolation to get the equilibrium climate sensitivity. There are, of course, some problems with this approach, and there are generalizations, but this is pretty much the standard approach for estimating climate sensitivity in models. If we want to use real data, we can't do this because we don't have data. At least we don't have long records of this imbalance at the top of the atmosphere. So we want to use time series, and then it's instructive at least to look at some very, very simple climate models. So the simplest climate model that we can imagine is this one-box energy balance model for our planet. It's obtained by simply saying that the change in the heat content of Earth is given by the difference between ingoing and outgoing radiation. The incoming radiation is given by the albedo and the solar constant. The outgoing is roughly proportional to the 4th power of the average surface temperature. If we say that the heat content is some heat capacity times the surface temperature, then we obtain a differential equation for the temperature. We can look for fixed points and linearize. And if we linearize, we introduce this feedback parameter lambda. And so we get this simple equation that is exactly the same that I showed you before. Now I introduce this term f of t, which we call radiative forcing. It's the changes to the radiative balance from, say, emission of greenhouse gases and volcanic eruptions and stuff like that. So this linear equation, we can solve it. It's linear, so why not just use the Fourier transform? Take the Fourier transform of both sides of the equations, we collect the terms, and we see that in the frequency domain, the temperature response to the forcing is given by a product of this function g hat of omega and the Fourier transform of the radiative forcing. And for this simple equation, we have this nice and simple formula for this g hat of omega. And it's sometimes useful to introduce this parameter tau, which is the heat capacity divided by the feedback parameter. And if we take the inverse transform and use the convolution theorem, we see that in the time domain, the temperature response to the radiative forcing is given by a convolution of this function g, which I will call the response function, which in this simple example is an exponential, and the radiative forcing f of t. And if we let time go to infinity, we see that the equilibrium climate sensitivity is inversely proportional to the feedback parameter. Of course it is, because you can get that directly from the equation as we did before. Now, if we drive a climate model like this with white noise, it's like a stochastic differential equation like this. We know now that this defines a stochastic process called the Ornstein-Uhlenbeck process. It can also be written like this, a convolution of the response function with white noise, because it's just considered white noise to be the forcing. And we have these formulas for the covariance and the power spectral density. The power, in particular, the power spectral density is the square of the Fourier transform of the response function. And these are formulas that hold in general, not only for an exponential response function, but if we assume an exponential response function, we get these formulas. For instance, the variance of the temperature fluctuations is inversely proportional to the feedback parameter, just as we saw before. And we also see that this model predicts that the power spectral density of temperature fluctuations should follow this Lorentzian shape. Yeah, this is just a remark. All you need to derive these formulas are these what we call white noise relations, which is basically saying that my noise has zero mean and is uncorrelated. This is kind of essential for this to work. Now, imagine a situation where we both have some known forcing. We can call it deterministic forcing, like the red curve in the top right here. We have some data on the radiative forcing, but we also have some noisy perturbations of the system. In that case, the temperature response will split into two terms. One is the response to the known forcing. The second is a stochastic process, the response to the noisy forcing. And if we have data on the deterministic forcing, and we also have some data on the response, like an instrumental temperature record, then we can use this to estimate parameters in this model. There are several ways of doing it. And my favorite method here is like a maximum likelihood method, because for any set of observations xt1 up to xtm, we can write down an explicit formula for the joint probability density function, which will now depend on the model parameters. I just let theta here denote the model parameters. What enters into this formula is this mean vector mu, which is the response to the known forcing, and you have this covariance matrix sigma, which basically summarizes the stochastic properties of the second term in the model above. Now, if we maximize this likelihood function, I mean, this probability, if you view it as a function of the parameters, this probability density function is a likelihood function. You maximize that with respect to the parameters, you get parameter estimates here. So for instance, you do this on the instrumental record, you get that the characteristic timescale of our climate system is 4.3 years. Now, of course, this is nonsense. If this were true, this would be the most important number in climate science. The problem here is not the method, it's the model, it's too simple. One of the ways to see that the model is not very good is to look at the power spectral density of temperature fluctuations. The model says that it should be a Lorentzian with a scale break at the frequency corresponding to this characteristic timescale tau. However, if we look at some real data, say look at the red curve here, which is the global mean surface temperature, and you look at the power spectral density to the right, you don't see this scale break. You don't see this 4.3 years. In fact, you don't see any characteristic scales at all. You might see the some signatures of ENSO in there, but you don't see any clear characteristic timescales. And in fact, this power spectral density is more consistent with a power law than a Lorentzian. You should look to the figure to the right here, which is a power spectral density on a larger range of timescales. This is obtained from several temperature records. Again, you see that it has this power law shape. And you could ask, I mean, what type of response function would I need in order to have a power law spectrum for the temperature fluctuations? And the answer is not surprising. You'd get that if you use a power law response function. There are serious problems with a power law response function. One of the problems is that the climate sensitivity is infinite because there's an integral that diverges. But we'll return to that. So what we want to do is that we want to consider more general models. So I keep this basic setup. The temperature response is two parts. It's a response to the known forcing, and it's a response to noisy forcing with the same response function g in both integrals. And there are a lot of very general formulas here. The equilibrium sensitivity of the system is the integral of the response function. And the covariance is still given by this nice formula here. The power spectral density is still the square of the Fourier transform of the response function. The variance of the fluctuations is proportional to the integral of the square of the response function. And then you have this fluctuation response relation that relates the sensitivity to the statistical properties of the fluctuations. And you see it's not the variance on the right-hand side here. The square of the equilibrium sensitivity is actually proportional to the power spectral density evaluated at the zero frequency. So it's actually the fluctuations on the very, very longest timescales in your system that is directly related to the equilibrium sensitivity. And that makes sense because equilibrium sensitivity is kind of defined asymptotically as time goes to infinity. In general, we can estimate parameters in the same way that I explained before. What I need is data on the response and some data on the forcing. Then I can use this maximum likelihood approach to estimate my parameters. In the case of an exponential response function, this would be this heat capacity feedback parameter and some scale parameter for the noise. For other response function, these will be other parameters, but I can use the same setup here. Or we can use the Bayesian approach to obtain posterior probabilities of the model parameters if we wish to do that. So one example of a bit more general model is this two-box model. Here, the second variable x represents the temperature anomaly in the deep ocean, and you have some energy transport from the mixed layer into the deep ocean. If you do some linear algebra on this system, you obtain a response function which is now not an exponential, but superposition of two exponential functions. This will give you two characteristic timescales. We can generalize this to look at, say, an n-box model, where you divide your ocean into n layers. You can either do some linear algebra on this system, or you can take a continuum limit, in which case the energy transport into the ocean becomes a diffusion process. You can obtain a linear diffusion equation. You can solve that equation. It's not very difficult. The point is that the temperature at any depth in the ocean is now written in the same form that I showed you before. It's a convolution with the radiative forcing. In particular, the surface temperature, which I show you in the lower left here, is a convolution of this response function g, which we have a nice formula for. And again, if you take this integral over this response function, you get that the equilibrium sensitivity is inversely proportional to the feedback parameter lambda. More interestingly, if you plot this response function for reasonable values, parameter values, it actually is very well approximated by a power law. So this could be like an explanation why we see power law spectra in the temperature records. And then we can cheat a little bit. We can just say, well, what happens if I just put a power law in here? I get some well-defined model. The second term here is not an Ornstein-Uhlenbeck process anymore. It's what we call the fractional Gaussian noise, which is a stochastic process with long-range dependence. But actually, this model here works, really well for describing the relationship between radiative forcing and the temperature response in, say, the instrumental record or in historical runs of climate models, as you see in the figures below here. Now, the problem, as I mentioned with this, is that if I want to get the sensitivity, equilibrium sensitivity here, I'll get the divergent integral. There's a workaround, and that is introducing what we call scale-dependent sensitivity, which is closely related to this idea of transient sensitivity that I discussed before. The definition is simply to take the absolute value of the Fourier transform of the response function. That will give me a sensitivity on that frequency, so on that time scale. And for the 1-box model and 2-box model, we have these simple formulas. And we see that if the frequency goes to 0, we get 1 over the feedback parameter, so we get the equilibrium sensitivity of the system. But for this model to the right here, where the response function is a power law, this diverges when the frequency goes to 0. But what we can do is that we can just evaluate the sensitivity at the finite frequency corresponding to the timescales that we are interested in when we use this model. So the model is not necessarily valid on all timescales, but it could be valid on the timescales that we're interested in. And in fact, we can compare. If we can take some climate model runs and estimate model parameters in a model like this to get the scale-dependent sensitivity. And then we can ask at what frequency do we have equality between the scale-dependent sensitivity and these Gregory estimates of climate sensitivity. And the result is not surprising. It's roughly a 1,000-year time scale. So this type of model would be useful up to that time scale. And in fact, if you take historical runs of climate models and you estimate scale-dependent sensitivity at this time scale, the results correlate across the model ensemble really well with the equilibrium climate sensitivity obtained by this Gregory approach. All right, so that was some ideas about climate sensitivity. Now, very briefly, I'm just going to tie these two things together. And you see there's a lot of similarities here in the concepts. So the idea here is pretty simple. If we have a system, we suspect it's maybe approaching a critical transition. Why not make some assumption about the forcing or the control parameter? For instance, as you see in the figure in the top right here, if we assume that the control parameter is changing linearly with time, we can take a time window between t prime and t double prime here. And within this window, we can use this maximum likelihood method to estimate model parameters. And if we estimate model parameters, we are also estimating the sensitivity of the system to the control parameter. So we basically fit models within each window. So if you look to the lower right here, the blue curves here are like realization of a fitted model within this time window. And we can now move the window, and we can vary the length of the window, and we can plot the sensitivity for as a function of time and as a function of the window length. So that's what you see in the triangular plot in the lower left now. I have time along the first axis and window length along the second axis. Red color means higher sensitivity, blue means lower sensitivity. You expect these plots to be quite noisy in the lower part because the windows are short. But you see here in this example that there's this tendency for more red and yellow as you move to the right. And this is an indication that you have increased sensitivity. This is showing the same thing. The triangle to the right is the same that you saw before, just in a different color scheme. And the figure to the lower left here is just plotting the sensitivity, estimated sensitivity as a function of time for different window lengths. And you see this increase in sensitivity, which we take as an early warning indicator of this, of a critical transition. At least we're detecting an increased sensitivity to the control parameter. Okay, let's try this on a real data set. So I just searched the literature and found one example here. So it's, and let's consider the Atlantic Meridional Overturning Circulation, the AMOC. There's a recent paper of Ditlevsen and Ditlevsen where they propose a data set that is supposed to be a fingerprint of the AMOC. So we think that the AMOC is slowing down, perhaps approaching a critical transition to an alternative state. So let's try to see if our method works on this data set. So if I assume that my control parameter is changing linearly in time, you see in the figure below here that I detect some increasing sensitivity to this control parameter in time, and we can take this as an early warning indicator. At least it's increasing for the first part of the last century. However, I'm making some assumptions here about my control parameter. So what we typically think of as the control parameter for a slowdown of the AMOC is like freshwater input into the North Atlantic. We might assume that this is changing linearly in time, but we can also play with some other assumptions here. So if we, for instance, assume that this the control parameter somehow is proportional to global climate change, let's just see what happens if I change my control parameter. I'll skip this one to say that it's proportional to the global mean surface temperature. And if I do that, essentially I'm not detecting any increased sensitivity at all. We can also play a little bit around with this and say, well, what if the control parameter is somehow proportional to runoff from Greenland? Well, we have some reconstruction of that data set going back to 1870. And if I assume that that's my control parameter, I actually detect a decreasing sensitivity to that control parameter. So this, what I'm showing you here is for this exponential response model. I can use, say, a power law response model and evaluate the sensitivity on decadal timescales. It's a little bit more noisy, but again, we see more or less the same thing. Finally, I just want to show you that there are also methods, very similar methods that don't require these running windows. One approach is to consider a model like you see here. There's this parameter phi here, which is closely related to the feedback parameter. So large phi corresponds to large sensitivity. You can use a Bayesian approach to fit a model like this to your data sets, assuming different things about your control parameter. If you assume that this phi can change in time, say linearly in time, you can obtain Bayesian estimates for this change. If I assume that my control parameter is changing linearly in time, I will detect a linear increase in this phi. So I'm detecting increased sensitivity. Although you see from the confidence bands here, it's not statistically significant. If I change my control parameter to being proportional to runoff from Greenland, and then I actually detect decreasing sensitivity to the control parameter. Again, not statistically significant. So to conclude, we're playing with some ideas how to estimate a state variable sensitivity to a control parameter through this maximum likelihood methods applied locally in time. What we observed so far is that the results are very sensitive to the assumptions that we make about the time evolution of the control parameters. We haven't worked enough on this to make any conclusion about any real systems, but that's what we observe. And we also have some methods for testing this null hypothesis, which in this case is that our system is responding linearly and stationarily to the control parameter. So thank you very much for your attention. I'm happy to answer any questions.
Great. Thank you very much, Martin. That was very interesting. I'm sure there's quite a lot of questions. Maybe to give people time to think about their questions, maybe I start with the first one, which is so I didn't fully understand. So the last bit was a bit quick for me, but very interesting. So your point was that without even any dependence on sort of like a parameter like the window length, you can test the hypothesis, like statistically test the hypothesis of a nonlinear response versus a linear response in the AMOC fingerprint. And the result was that there's sort of, you can't reject the null hypothesis of a linear response, both to temperature and to Greenland runoff forcing. Did I capture that correctly?
Yeah, so it's true. So the null hypothesis is a linear and stationary response. So that's what we want to reject. Now, the way we do it is that we then use a linear but non-stationary, possibly non-stationary model, and we allow this AR1 parameter to change in time, and then we get in the Bayesian setting we get posterior probabilities for the changing time of this parameter. We can't reject the hypothesis that it is non-stationary, right? Because we're not detecting, I mean, detecting a significant increase in this AR1 parameter would say that this cannot be, what we're observing cannot be reproduced by a linear and stationary model. We can't reject that.
You can't reject that what you're observing is produced by a linear response. Or by
that is true.
Yes.
We can't reject that it's produced by a linear response. It doesn't, I mean, we can conclude that it is produced by a linear response, but we can't reject it using this.
Yeah. So, but this is really nice because it also somehow, I mean, you know, like it fits to this recent paper by Mujib Latif, who also showed that sort of from the historical records, we cannot sort of claim that the current slowdown in the AMOC isn't just part of natural variability.
Exactly.
Yeah, interesting. Great. All right. I see the first question by Stephen.
Hi, Martin. Thanks a lot. I really enjoyed that sort of starting off with basic models that we all know and then sort of pushing them a bit harder and getting some interesting insights into things that people are trying to do. That my takeaway of which is that it may be quite challenging to get sensitivities out of natural variability. I was going back to your equilibrium sensitivity thing that you showed. I was wondering what the role is of forcing. The sort of Achilles heel of most efforts to get sensitivity from any observed record is not having a detailed knowledge of the time series of the forcing. And I think the spectrum you get that looks like a power law may largely be determined by the spectrum of the forcing due to aerosol, solar variations, volcanoes, and everything else, even in the absence of CO2. And so I was wondering if you could comment a bit on that, and how it affects what you said.
So your first comment is absolutely true. If you want to use these methods to get some constraint on equilibrium climate sensitivity, the uncertainty in the forcings and in historical period is what's causing the problem. If you can just play with it. I mean, forcing is basically something. Estimates of forcing is something you get from models, and if you get different data sets from different models, this will largely affect your estimates. So it doesn't really work too well there. The second comment is that, I mean, in the Holocene, we have some reconstructions. I mean, the anthropogenic part doesn't really influence the power spectral density too much, because we can just go prior to the industrial age and estimate a spectrum. It will also look like a power law. I think, but of course, there are several papers which show that if you use like a 3-box model or something like that, you get 3 different characteristic timescales. And with the amount of data we have, you won't be able to distinguish something with like 3 humps and a power law. So it's more like a power law is it's a useful statistical model because it's quite accurately describes what we have with very few parameters. And I mean, a more detailed model will give us more parameters and would just be a nightmare from a statistical point of view. So one shouldn't kind of overemphasize the complex systems thing here when it comes to this power law. It's more that it's a very practical statistical model.
I guess what I was going to say, since I don't see any other hands going up yet, I'll just take the floor back again, is that I suspect that if you had a accurately measured time series of a system with really no variability in external forcing at all, it might actually start to look like a Lorentzian with a characteristic time scale of the sort of deep ocean turnover, which is roughly the time scale that you were extrapolating out to in order to connect up with ECS. Does that sound like it might be reasonable?
Yeah. Well, we have the control runs of the climate models, right? So a control run of a climate model, there's no forcing at all. And if you there are some long control runs, you do a power spectral density of that, you don't really see any. You actually see something that's more like a power law, surprisingly. Okay. Yeah. But of course, I mean, there are some characteristic frequency. I mean, the one that sticks out is is ENSO. That's kind of the only kind of characteristic peak that you can see in those kind of spectrum. Yeah.
All right, Hannah.
Oh, thank you. Thanks for a great talk. I feel like I've learned a lot, and I'm not at all an expert in this area, so this is going to be a very naive question. I was really interested about this discussion of the forcing and why it's difficult to estimate that from observation. So, I mean, could you elaborate a bit more on why you need the model? Why can't you just look at the top of atmosphere energy budget in some way?
Oh, you can now with satellites, right? Okay. The problem is that the data sets, I mean, if you want sufficiently long data sets, if you want, say if you want forcing data that matches the instrumental temperature record, you have to go back to like 1850 or 80. And you don't have that kind of data, top of the atmosphere balance going back that far. There are people who tried to done this from the data that we have from the satellite measurements. I mean, since 1979 or whatever. And I mean, right now these satellite records are just too short to improve the situation. So you basically, the uncertainty is exactly the same that we have from the model ensemble. So it's a good question. When the satellite records become longer, they will probably be very useful. Yeah.
Okay, thank you so much.
Sebastian.
Yeah, thanks. Yeah, very insightful, everything. I have a question about part 1, where you mentioned that so in a very simple double fold model, so there's this relationship between sensitivity and recovery and variability. And you mentioned in higher dimensions, something doesn't work. And maybe you could show that slide. So I wasn't sure what exactly is violated there. And it's really interesting because I'm looking at vegetation models, and something like that happens when you have more plant types than one. But there, so there the recovery rate is not related to the sensitivity anymore, but it's still related to the variability. But here it seems different.
Yeah. So in the basic setup that what holds in general for the type of models that I consider here is that the equilibrium sensitivity is actually equal to the integral over the correlation function, which equals the power spectral density at the lowest frequencies. Now, for the simplest models, where there's only one characteristic timescale and you have a Lorentzian spectrum, because the Lorentzian spectrum kind of goes flat in a simple way. So for this particular spectrum, it turns out that the power spectral density at the zero frequency and the variance, which is like the integral under the of the power spectral density, are proportional to each other. So it's a special case that the variance works for this very simplest model. It doesn't work in general. It doesn't mean that there's not a relationship between the fluctuations and the sensitivity. It's just that the variance is not the correct way to measure the fluctuations if you want it to be proportional to the sensitivity. I think that's the, So you're not violating.
What about the lower left side, so the sensitivity and the return rate? But that seems to still work, right?
For this particular model. Yeah, so I constructed a model where basically it's the second equation here only has an effect in a sense on the inertia of the system. The fixed points are completely given by the first equation. That's why it's still working. So that's also a special case. That's also a special case. Yeah.
Yeah, but in general, it would not work necessarily.
Generally, it would not work like that. Yeah. That's true.
Mm-hmm.
Yeah.
Mm-hmm. Thanks.
Could I maybe quickly also sort of a question of understanding, because I don't see any other hands raised right now, sort of come back to Hannah's question. You had this one slide where you showed this really nice reproduction of the temperature record in terms of a forced response.
Yep.
And there I also wasn't quite sure understood the...
So I had two. So I had this one, and I had one that was even better. Maybe the other one.
Yeah, yeah, maybe it doesn't even matter so much. But so I was curious how you. So you said so it's Hansen forcing. So you take this reconstruct. So this is top of atmosphere radiative forcing, basically that you're putting in here.
Yeah.
Okay. Yeah. Okay. Then that's
nice. Yeah. So I mean, there are several ways obtaining, forcing, how much forcing, the forcing is actually something that is produced in the models, right? There's some atmospheric physics here. So if you prescribe CO2, different models will produce different forcing because they implement the atmospheric physics differently. And that's part of the uncertainty here. So you could kind of change the picture and say, well, we want to measure sensitivity to CO2 directly, or even more interestingly, you want to measure sensitivity to emissions, which would be kind of even more useful. And that's maybe what you should do now with the type of Earth system models that include carbon cycle and all of that. But that will give you another layer of uncertainty, because you get the uncertainty in how how you go from emissions to concentrations, which is also varies between models.
Yeah, very nice. That makes perfect sense.
Mm.
And maybe if I may ask another question, could you comment a little bit on the, since we're looking at factorial Gaussian noise, so dB is Ornstein-Uhlenbeck noise, if I got that correctly, right?
dB is white noise here.
dB is white noise. Okay.
Yeah.
So could you maybe comment on the sort of like the role of like having additive white noise in this model versus having additive red noise, or generally colored noise towards like strong memory in the noise and so on? Maybe could you comment on that a little bit?
You could write, you could add another equation, right? You could put in red noise here, and then have a second equation that describes how you get red noise from white noise, and then you get a system of equations. And basically the same setup would work, but it would kind of involve a little bit more linear algebra in order to get the response functions, and things would change a little. But you're absolutely right. If we consider, say, we are studying the response of components of the climate system to control parameters, and if these control parameters are, say, temperature, if this is temperature, assuming that temperature is white noise, is not that accurate at all. So it's a very good research question if you want to study early warning signals to change this this assumption. Yeah, absolutely.
Great, thank you. Are there any further questions? All right, if that doesn't seem to be the case, then we might actually manage to finish in time. Again, thank you so much, Martin. This was really interesting. So we're going to put the talk on the recording on the website. It would also be great if you could send us your slides, if you don't mind. So we could put them up as well. And then, so we have a Christmas break now, and we will continue in February with a talk by Pierre Gentin from New York. So thank you very much, and see you all in the next year. Take care, and lovely holidays. Thank you.